of you may have heard the Fermi-Golden rule, things like that, but the formula first derived was by Dirac, if I trace it correctly. So on this about 8 pages or so, I want to derive equation 13 for you, okay? And it is a rather, conceptually a rather nice exercise. So here, my goal is to arrive at the key equation that you already saw and introduce the key idea behind time-dependent perturbation theory. So very quickly, remind you of the problem. The problem is we have an atom part H0 in which the atom eigenstates are all known. We know 1s, 2s, 2p, so that is the part of atom thing. We know all this. And then there is an interaction part that is time dependent, usually switch on from some time called 0. Then the question is, we want to find the state, the probability of finding it in some state after the perturbation is switched on. Negative time, the perturbation is off, okay? So let me motivate Dirac's first equation, because after the first equation, everything follows nicely. I already did a little bit in the last hour. The point is that if the perturbation is not there, that is to say H0 alone, we know how to handle time evolving mechanism. H0 is time independent, so we know the standard procedure. Let's say there is an initial state. It need not be in one of the eigenstates in general, so let me just to state it generally. At time equals 0, it is a linear combination of the atom's eigenstate. So in shorthand, it is this, okay? And let's say these are knowns. You know the composition, you know the weighting, all right? Now, if we don't have the perturbation, H0 only, what is the wave function at time t, the state at time t? Easy, right? Each one will evolve with its own time evolution factor. The nth one has its own eigenvalue, so this En, okay, match with this nth eigenstate. So in one line, we answered the time evolution question. You give me a time t, 0, you give me all this coefficient, I return you this. It is the same coefficient, only every state evolved in time in its own way. Okay, this is just like EM wave dispersion, right? You have a wave packet containing different frequencies. If it's traveling in a matter, not vacuum, then each one will have its own different speed, and therefore it will disperse slightly afterwards. The analysis is component by component, let it go, at some time t, add them together. So this is the same thing. So, and then you ask, what is the chance of finding the state at time t to be in state n? You read this thing out, the coefficient, take a square, but this thing will be 1, okay? Therefore, you will get the same chance, okay? So the chance will not be altered because there is no perturbation. You only have this H0, okay? Then the meaning follows is if you take the energy expectation value, it will not change, okay? Because you don't have time-dependent part in the Hamiltonian. So everything is nice if you don't have time-dependent perturbation, okay? But now it's not like that. You have this, okay? Therefore, this will not work anymore, right? Now, let's inspect A3. A3 means this coefficient will take on the same coefficient as in time equals 0, okay? So let me make the logic straighter. If you only have H0, this coefficient will not change in time. Okay, follow me? Now Dirac used this statement and think one more step. In the presence of this perturbation, the effect is that it will lead to some time dependence in this coefficient. Okay, and that's what Dirac did. Okay, now that logically is very nice, straightforward. Okay, this term only, this works, and this is time independent. Now, if you have this, let's assume this works, but you have time dependence in the coefficient, and all this time dependence must come from the perturbation term. Okay, so that is what Dirac did. So this step is the most important step in the whole theory. This is called the Dirac's method of variation of constants. By that mean the constants become time varying. Okay, now mathematically it is exact, because this at time t forms a complete set. So what Dirac did is that the unknown wave function at time t, even in the presence of time-dependent perturbation, can be expanded using this atom state at time t, but now you must invoke a further time dependence in the coefficient. And this time dependence entirely, solely come from the time dependent H prime term. Okay, so follow the logic up to here. Okay, I mean A4, that is the starting point and the most important formula. Do you understand? At least, can you make sense out of it, right? Okay. Now, what is the next question, right? You learn physics, don't learn the facts, right? You learn the way of thinking, all right? Now, then what is the next question? We introduced the time dependence, and we know that is entirely related to this term. So we want to solve for the time dependence, an of t for all n's, all states of the atom. Okay? If we can look for that, then an t square will be the chance of finding the atom in the atomic nth state at time t. Okay? Under the influence of H prime, right? So the problem becomes, look for this, okay? In order to look for that, we need how this change in time, for the reason we know the initial value because at time equals 0, we can have the initial state, that is to say, AN at time 0 is given. So it is an initial value problem. To solve an initial value problem, we have to look for how AN of t evolves in time. By that, we mean we need a differential equation in time for the coefficient so that it can grow or it can decrease, okay, for the initial state. It can grow from 0 to some finite chance, okay? So far, I have been stating the problem in completely general way, okay? Meaning the initial state, initial value problem can be given as you give me all the values of AN at time 0, okay? A few of them can be non-zero, that's fine. That will be a linear combination of states. I can still look up how H prime change all these values later time t. But one special case interested us most is the experimental or the question we posed. It is some state called 1, okay, state 1. That state can be initial, meaning, okay? State 1 is certain at time 0. That is to say, at time 0, the system is certainly to be in some state called number 1. And we want to look for what happened after this is switched on, and then at later time, all the other state, what is AN of t, okay? Now that is one special case of the initial value problem, okay? So we move on. Now we know what we want to get, right? This is the assumed form. These are the unknown time-dependent coefficients. We want to set up this equation so that we can integrate in time, make use of the initial conditions, then we solve the problem. Okay, do you follow me? At least the big picture, the path. Okay, so let's do it. As I said, time-dependent problem is easy because there's only one equation to work with. Time-dependent Schrodinger equation, okay? So this is the time-dependent Schrodinger equation, including the effect of the perturbation term. What's next? Plug Dirac's expression for phi in the left-hand side and right-hand side. Okay, do you follow me? Let's look at the right-hand side, right? You have d dt. Therefore, for certain, you will pick up d a and dt. You get all this thing in one equation. Okay, do you follow the idea? Is that fine? Okay, so now some longer formulas appears, okay? But I try to make it as friendly as possible already. So let's substitute Dirac's expansion into the left-hand side and the right-hand side. So I will still do it in a slow motion, okay? Left-hand side. Okay, now the expansion, first thing, you have a H0 that will operate on every term like this. The coefficient, though unknown, is a number. Okay, we are looking for this number, so this can go across the atom Hamiltonian. So the only thing that the atom Hamiltonian sees and can operate on is in the expansion, the atomic energy eigenstates are used. Okay, so in black, I highlight this part. When you plug in the expansion into the left-hand side, the first term. The second term, my expansion is all this in black. I have the perturbation. Okay, so first line seems trivial, I hope. Then phi n's are energy eigenstate of the atom H0. Therefore, that will return me the eigenvalue of that state, En phi n. All right, nice. Second term can't go further. I just repeat it here, okay? Done. Right-hand side. IH bar ddt, okay? Then the enemy is time, so let's look for time. There is one time here to d, there is another time here to d, okay? Follow me? So there will be many terms in time to d. The first one, do the derivative of time up in the exponential. For every time derivative, you will bring down this prefactor of time. And exponential cannot be d away, so it remains. Okay, so follow this time. The second one is the coefficient, and that is the leading role of the whole theory. We want equations for dA and dt, and now we started to see this kind of thing coming out. So we have this d coefficient dt, the remaining thing, just write it there, okay? Now, h bar cancels h bar, I minus I is a good one, all right? Now, the first term is this. It happens on the left-hand side, you see the identical same term. That should be, because Dirac is very clever. He used this already, evolved it by the H0 wave function for the expansion. And the H0 inference is already built in. And because of that, you will see the first term on the left-hand side and the right-hand side cancel each other, okay? Summary, after we plug Dirac's expansion into left-hand side and right-hand side of the Schrödinger equation, we only get one equation. On the left-hand side, this term only. On the right-hand side, this term only. Of course, this is the sum over all the eigenstate. Many terms equal many terms, okay? So we are done. So this is the equation after plugging the expansion into Schrödinger equation, okay? So far, any question? This is something that every student can understand, okay? No one should be left out. Any questions so far? You know what's being done? Hello? We are halfway through. We are nearly at there, okay? 得唔得？有冇問題？冇問題。Okay? Now, at this point, I worry some of you don't like to see, wow, on the left-hand side, maybe 180 terms, on the right-hand side, 180 terms, this 180 terms equal that 180 terms. Woo, hard to see what's going on, okay? So to make life easier, and actually, without loss of generality, it's still quite general. Let's see Actually, we have n equals 1, 2, 3, 4, 5, to, well, basically to infinity. I try to depict all of them here. But what if we just pick one of them to call it number 1, state 1, and find another one. It need not be the nearest one. You can find any one and call it 2. Okay. So from many, I pick out 2, come out, and then instead of focusing on infinite many, I just focus on 2. Okay. I will call it 1, 2. So behind the scene, the corresponding atomic eigenstate will be called phi1, energy E1, phi2, energy E2, respectively. Of course, what I call 1 need not be of lower energy. It could also be what I call 1 is the higher energy, the 2 is the lower energy. It doesn't matter. So far, it's completely general. Okay. And that may allow us to see the equations clearer. So from this point on, let's single out 2 states. Then pretend it is just 2 states in our system. Then this equation will have 2 terms. The sum will be n equals 1 and 2 on the left-hand side and right-hand side. So explicitly, my page can allow me to write it out, okay? Otherwise, my page is too narrow. So in two levels only, well, 2 states, I would rather say. Then the left-hand side is A1, phi1, E1 plus A2, phi2, E2, okay? So I have these 2 terms. That is the left-hand side, okay? Follow me? Right-hand side, I only get 1, 2 here, okay, for the n, okay? Therefore, I will have A1, the perturbation, phi1, and the phase for E1, and then the similar term, A2 unknown, okay? There. So what are the unknowns? Let's take account, okay? We want to set up equations, dA1 dt, dA2 dt, and we are given some initial conditions, A1, A2, and we want to solve for A1t, A2t using the time evolution equation, okay? So next goal, we want to extract equations for dA1 dt and dA2 dt. All right. Now, at this point, you see they are all coupled. They all appear in one single equation. All right. Now, I should mention equation A6 is completely equivalent to the Schrodinger equation, time dependent, because all the steps here, there are no approximation made. We are just representing the Schrodinger equation in the basis chosen by Dirac, this one, okay? So A6 is equivalent. Equivalent in Chinese is 等价,等价的. That means no one is more superior than the other, okay? They are the same. They represent the same physics, okay? So in a sense, if we are only considering 2 states, this is complete knowledge from quantum mechanics, no approximation yet, okay? Now the goal is to isolate an equation for dA2 dt. Okay, you understand the question? I want an equation that dA2 dt stand out on the left-hand side, okay? Do you see immediately that is very possible? Now, you take phi2, multiply into phi1, the term here, you know, phi2 star, phi1, integrate over space. by orthogonality. This term will be gone, right? Then you have this stand alone. Okay, do you follow the idea? Okay, similarly, if you want to find a rate equation for A1 alone, multiply every term by phi 1 star, do the spatial one, you kill the second term. Okay, so life is easy, right? Straightforward, right? So don't be scared. If you understand what I'm saying, you already done that. Okay, so now I want a standalone equation for dA2 dt. Therefore, I left multiply psi 2 star into every term and do an integral over space. Okay, so that are the two steps. So I did it in one intermediate step. The term here, phi 2 star, okay, normalized, because normalized, you get a 1 after integration. So you still have this time phase term remaining. So the left-hand side will have that. The right-hand side, now interesting physics starts to come out. Two terms, psi 2 star, integrate over space, okay? Then you will see you have a term that is relating 1 to 2. The second term is 2 to itself, okay? Now, referring to the old perturbation theory, time-independent one, we would have called this H'21, the element, you have an element, okay? And then this is the 2 element. Also, just to remind you, H' also has a R dependence in it in addition to time, because I just want to emphasize sufficiently we are doing time-dependent perturbation, right? But don't forget, there is a R, the matter part in it. Therefore, there are integrals to do. Now you see that spatial integral that will give us selection rules, right? Okay, it's there already. Now, the last step, move this part, this phase, from the left-hand side to the right-hand side, okay? Now, this is minus to the other side becomes a plus. Therefore, the first term, you start seeing this difference in energy. Now, energy selection start to emerge. E2 minus E1, we pick out two states. E2 minus E1 is the difference in energy. It is there. It started to emerge. In the second term, because it deals with the second state, the same phase factor, but when I take it to the other side, it becomes a plus, kill each other to become a 1. So I don't have a phase factor for the second term, okay? So now done. This is the equation that we look for, dA2 dt, okay? So I pause here to see whether this is the key step, okay? Any question here? Xỉn不xỉn啊？得唔得啊 ？OK 唔 OK？Is that OK？ Do you believe that you can close all your book and then you do it out just as Dirac did? It's very possible, right? Year 3 students, right? Okay, if you know the path, if you follow the logic, all right? Now, how about isolating dA1 dt, what we usually call the initial, okay, 1, okay? Of course, you can do it, follow the same thing, right? But now you multiply left, multiply by phi 1 star to the part, okay? You can do it again, but if you inspect this, probably you know the pattern. So the end result is you have this on the left-hand side. There is a term that is relating one to itself, and you don't have any phase factor. So this is the same form as that. And then for the other state, you pick up this unknown coefficient, then this energy difference will appear because this has to do with 1 with another state 2. Okay, then you will pick up this particular energy difference. Okay, and then there is a spatial integral relating how the perturbation can connect to and affect 1. Now, this is the influence on 1. Okay, now go home. Well, you are at home, right? So stay at home and then try. What if we have 3 states? 1, 2, 3. Okay. Either you start off from the general equation A6, write down it in 3 terms on the left, 3 terms on the right. You do this left multiply, integrate 3 different states, you get 3 equations. Or simply by inspection, can you write down a term for E3 minus E1, something like that there? Do you understand? Probably you don't need to derive it again, right? Okay. Therefore, you may also want to try to write down the general equation. Okay. For example, IH bar D2 dt, if I want a summation over n, okay, for all the other states, what this term will be, right? So just 1 can be any n, and then you sum over n, that will do, right? And then 1 term will be different. That is its own self, okay? But even the form is the same, only that E2 minus E2 gives you 0, and that term, that phase term is 1, okay? So now do you see through the problem? I mean, that is more important than keep on deriving things. Okay? So now let me remind you one more time. We got these 2 equations from the time-dependent Schrodinger equation. Every step is exact. Okay? That is to say, no approximation yet. The equations are equivalent to the full time-dependent Schrodinger equation. Okay? And at this point, we have not made use of any initial given condition yet. Okay? The point is, we have rewritten time-dependent Schrodinger equation in the Dirac expansion. Now we are ready to look for the coefficients. We know the rate, and then we note we have the unknown coefficients on the right-hand side as well. Okay? Now, let me remind you again, there is one particularly useful initial condition in our context of atom interacting with light. It is, at initial time, the atom is certainly in state 1. So 1 will be our initial state. Okay. And therefore, it is certain that it is not in state 2. So A20 is 0. And then we switch this on from time equals 0. And then we ask, any chance that it will be found to be in the state 2 afterwards? Okay, initially, it's certainly not there, but with perturbation, will that be there? Okay, now notice that that has nothing to do with our formulation yet. This is a supplementary information so that we can make use of that to solve these two equations. Okay, this is not an approximation, this is a given condition, initial value problem. I emphasize this because I want all the students to be able to trace where does the approximation enter, and this is the place. So far, is completely general, okay? We follow the spirit of perturbation. In the previous time-independent perturbation theory, we know one thing. If we use the 0th order solutions on the right-hand side of the equation, then we can get the 1st order solution coming out in the equation on the setup from the left-hand side, okay? That is exactly what we are going to do in the next page, okay? So the idea is the following. As I mentioned several times today, if we don't have the perturbation, that is to say, the 0th order solution will be simple. Given this initial condition at time 0, at time t, A1, okay, is again 1 because the time dependent state will be simply that. According to the Dirac expansion, that is to say, A1 coefficient is 1, A2 coefficient will remain 0, okay? So, the initial conditions turns out to be the 0th order solution. Okay, do you get this one? 0th order, we mean H prime is not there. Okay? So, this 1 and 0 is the 0th order solution. Okay? So we are going to do the following rather lazy thing. We take this and say, we only want 1st order perturbation. So I will plug A2 0, A1 being 1, and then we got the equation for A2 dA2 dt. That will be the 1st order time dependent perturbation theory. Okay, very simple. So that is the idea. Okay, so I did that. And then the second term disappear. The coefficient A1 here is 1. So the A2 dt equation becomes this. Okay, so I pause here to see whether you understand where this is the very first approximation that we did, okay? This is how we get a simple equation for the coefficients, okay? And state 2 is where the atom was not there, 100% certain. Now, if the right-hand side is not 0, then we see A2 can grow with time from 0. So later time, there may be some probability finding the atom in the state number 2. That is the whole picture. Do you follow? Okay. Okay. So now let's do one more step, then we are done. Okay. This is dA2 dt. So I flow the dt to this side, do an integration over time, then I get an expression for A2t, right? This is the differential integration relationship. Okay, so I did that. I use the blue color to represent this time integration, all right? Because we want the answer at t, so for the integration, we must do from 0 to t. So this t goes with this t. Therefore, my integration over time, I better use another dummy variable called t prime. Okay? So I throw this in. I see a time that I can integrate over. Now cosine omega t prime, dt prime. Okay? So after doing that, this is my final equation. There are two. At this point, I don't know what is small, what is long. At this point, at least, okay? Then later on, when we see some result, then we can see whether what do we mean by long time, short time. Is that okay, Ling? Okay, but this is a good question. For all this to work, we better be self-consistent. We better have this thing remaining small. That is the spirit of perturbation. Okay, so two answers, Ling. At this point, T is left general, but for the whole idea of perturbation to be valid, we don't overuse the result. Okay, so after doing calculation, if A2T remains small, well, less than 1, then that's fine, because this is probability, you know? We sum up all this A and T, it should be 1, normalized. Okay, get me? All right, very good physical question. Okay, now this is exactly the key question in the last, the key equation in the last hour, equation 13, that I claimed by waving my hand in the poor man's discussion, in the big picture rough discussion. Now I derived that for you. This is exactly that same equation. Okay. Now you see the 0 here because we assume the switch on time to be 0. I'm asking the question at time t, so the perturbation works from 0 up to time t, and then I get the answer and analyzed. When I do the integration, you may wonder, there should be an integration constant somewhere, right? Okay, but I know the initial condition. The initial condition is that constant is 0. Okay, so actually I make use of it when I write down this equation. There's a constant that happens to be 0. Okay, so final punchline. As I already mentioned last hour, but very roughly, there are two integrals. First, it has to do with the initial state, final state, and the perturbation part that is R. Remember, this is R dot field, okay? This is the position of the electron. So you will pick up a initial state, a vector R, final state. Okay, you will pick up some integral like that. depending on initial state, final state, X in between, Y in between, and Z in between, whether this is zero, non-zero, you can determine whether this transition is allowed or forbidden. Allowed means it is not zero, but it can be small, right? It not zero, it need not be big. That determine the brightness of your spectral line. Okay, if it is zero, the spectral line disappears. Okay, unless you use other experimental condition, okay, strong field, very sensitive detector, then you are beyond the electric dipole mechanism. There is another integral, the time integral. Okay, there is a time part cosine omega t to go with this that will give you the energy criteria. H bar omega should go with this difference. Okay, common sense thing you know in the past, but now work out from Schrödinger quantum mechanics, pretty nice. Okay, so to be very explicit, spatial and time integral, this will be the spatial integral that you will do. So the R1, okay, and then there will be a time integral that we need to do only when both are non-zero. Okay, even this is non-zero, your incident frequency is wrong, you don't see anything. Makes sense, right? Okay, so even your frequency is right, but the transition is not allowed, you see nothing. How nice, okay? All in one line, okay? So this is basically the most important two equations, actually one, but this is general, this is written out very explicitly. This is a vector dot into another vector, there's a field, okay? Well, some of you like theory too much, then you may wonder, hey, you always talk about the empty state, the state 2 that is not there at time 0, you want to look at the transition probability. What if I look at the original occupied one? Can I get something like how this probability evolve in time? Can I see that it is lowering? Okay, let's see. Inserting the zero folder approximation, we will pick up this dA1 dp. Now that is the 1,1 matrix element. That is the governing equation for first order. Okay. Now several points. Very often, if you go from 1s to 1s, you put an R in between to integrate. That is 0. Okay. So very often you will find 0. Okay. And then even so, even if you represent this integral by 1,1 something, you can formally solve this A1t equation by doing the integral. Okay, so just like what we did, but there is an integration constant that is not 0 now. The initial condition is 1. So this is the formal solution after you do the integration. And that is this thing expanded and retaining the first term. So we anticipate, okay? So if we have another term, that is just the exponential. So conclusion. In conclusion, the original state that is 100% there, if you analyze this equation, the first order equation, you will find something like this. It amounts to a further phase in the term. And therefore, this A1 will remain square, will remain 1. All right. Of course, at the end, you can normalize the whole equation and you will find this actually slightly decreasing. But at least within the first order perturbation, time dependent, A1 magnitude is not going to give you a change. That makes sense. Perturbation, right? We mean A1 is still more or less 1, but we want to look for whether the other A, A2, A3, A4 will become non-zero. That is the point, okay? So usually we don't need to look at A1T equation. So I will end this part, okay, with a few references. For those of you who like to know more about time-dependent problem in quantum mechanics, Griffins has a chapter. What I discussed is part of the chapter. As I said, there are other things like slowly turning the things on. A very good chapter in this very complete book, Branson, Quantum Mechanics. And for those of you who like the applied physics part of shining at night, laser, things like that, try this. Yarif, a Caltech professor who are very famous in quantum electronics, things like that. He wrote a very simple book introducing quantum mechanics and its applications. It started from nothing, assuming students don't know any quantum mechanics, and at approaching the last part, doing some very fancy quantum electronics problems. Okay, it's a Caltech textbook. So that complete the derivation. If you can follow it, congratulations, good. If you don't worry. All we will do is to pick up from this equation, that is to say, from here, and start analyzing the consequence. Why do we have stimulated emission, absorption, selection rules, energy criteria, and how can we get transition rates, the per unit second, per second, okay? That is a quantity. The transition probability per second from this formula. That we will do next Tuesday, okay? So long for now. If you have questions, state here. I will answer your questions before I leave, okay?